Hello students, in last video we discussed the inductive effect, nothing but that is a permanent effect. Okay, so after that another we have the permanent effect, that is a resonance effect. So to understand the resonance effect we should come to know what is the resonance structure before that. Okay, so here we are going to discuss what is the resonance structure. After that we are going to come to know what is the resonance effect. Now let us see what is the resonance structure means. Here if you see the structure, here is the structure of benzene. Okay, now if you see the structure here, I am going to draw the complete structure of benzene in a two ways. Okay, so if I assign the label as it is a first carbon, second carbon, third, fourth, fifth, sixth carbon. Okay, for the same atom I am giving the same numbering here. This is first carbon, second, third, fourth, fifth, sixth. Okay, now here if you see here in between carbon first and second you have the double bond. Okay, whereas in this case what happen, you have the single bond. Okay, here in between carbon second and third you have the only single bond, but here we have the double bond. So here if you see the bond length of carbon carbon in the benzene, if it is only single bond, okay, if it's single bond it should be 154 picometer. Okay, or if it is only double bond mean it should be how much, 134 picometer should be there. But in case of benzene it is neither 154 picometers, it is a nor 134 picometers. It has the distance how much means carbon carbon distance we have 139 picometers. It is a what, the value is intermediate between the 154 and 134. Okay, so here what is the given as per the figure 1. Okay, here this is a figure 1 representation. Benzene should exhibit two different bond lengths due to carbon carbon single and carbon carbon double bond. Here you can see, okay, simply you can write here we have single bond, double bond. Okay, however, as determined experimentally, benzene has a uniform carbon carbon distance of 139 picometers. So what happened here, you have the carbon carbon, but only one bond length is there. Okay, if you see here, according to this structure what happened, he should have only first he should have single bond and double bond length, but throughout the structure we have only one bond length, that is how much is there, 139 picometer is there. Okay, so how you are going to explain this phenomena or this existence of only single bond means, you can explain because of presence of resonance structure. So here you can see here, according to the resonance theory, the actual structure of benzene cannot be adequately represented by any of these structures. Rather, it is hybrid of two structures 1 and 2 called resonance structure. Means here, what is the meaning of this one? Here you can see, okay, resonance structures means here. So here if you see here, so if you how you are going to explain this existence of only one type of bond means, here as is shown the molecule in benzene, it the double bonds are not going to stable like this. Okay, so here what happened, sometime you are going to find the double bond between the what, first and second carbon. Sometime what happens, it's going to convert as a single bond and you can see the double bond at second and third. Here what happens, second third having the single bond. Okay, so simply what I want to convey means the pi bond in the molecule is not constant. It is going to what, move around all the carbon atom. That's we are showing as our resonance hybrid. Hybrid means what, as you know very well. For example, hybrid fruits means what, whatever the required quantity all are present in one fruit. Okay, for example, you need the more pulp, you need more sweetness and more seeds, whatever that depends on the fruit. Okay, so all are present, that is called, we are calling the hybrid. So all the, for example, first structure I can write, second structure also I can write. Okay, so these are all you can write in the one structure. This is called a resonance hybrid. So finally, why we are going to get the only single bond, only one type of bond in the benzene, even though having the one single bond, one double bond mean, because the pi bonds are not localized. Okay, localized means what, it is a constant. Okay, it is not localized, they are the delocalized. Means delocalized means what, they are not constant, they are moving all the carbon around the moving all the carbons. That's why we have the only intermediate carbon distance, that is 139 picometers is there. Okay, so this is a structure 1 and structure 2. These are called what? Resonance structures, and this is called what? Resonance hybrid. Means these two structures you are going to show in the one form. Here this dotted line indicating means what? The pi bond is present in between all the carbon atoms. Okay. Now let us see the second example. We have the nitromethane. Okay. Nitromethane, which can be represented by two Lewis structures. That is the first and second. There are two types of NO bonds in this structure. Here we have the two types of NO bond. Okay. So if you assume this is first oxygen and this is second oxygen, what happened in between the, here we have the only single bond is there. But here what happened, if you see this is first oxygen, second atom. Okay. So here what happened now, this oxygen atom having the double bond and this having the what? Lone pair of electrons. Nothing but it's converted as what? Single bond. So I am here labeling as a first and second. Okay, first and second oxygen atom. So nitromethane, which can be represented by two Lewis structures. You can represent this is the first Lewis structure and this is a second Lewis structures. There are two types of NO bonds in present. Okay, here you can see this is a NO single bond, this is NO double bond. So however, it is known that two NO bonds of nitromethane of the same length. Here you are able to see the single bond, double bond. So what we expecting, single bond length will be different and double bond length will be different. Even though having the two types of bond, but here we have the only single bond length, the intermediate between the NO single bond and double bond. Here also the value between what? We having the intermediate between the single bond and double bond. So the actual structure of nitromethane is therefore resonance hybrid of two canonical forms 1 and 2. So these are, we are calling it our resonance structures or canonical structures. Both are same. So here the structure is not going to stable like that. We have to write the resonance hybrid. Okay. Here resonance structures, if you see here, the resonance structures, canonical structures or contributing structures are hypothetical and individually do not represent any molecule. So just now we told resonance structure, I am writing the benzene structure what? Sometime writing the benzene structure like this, means the double bond is present in the first and second carbon atom. Sometime I am writing like this. Okay. So what happened, here you can see the double bond is present between the what? Second and third carbon atom. Okay. These are the what? Hypothetical structures. Simply we are going to hypothetical, not the real. Okay. So the following rules are applied while writing the resonance structures. So if writing the resonance structures means you have to follow some rules. What are the rules means here? The resonance structure should have what? The same position of nuclei and the same number of unpaired electrons. Okay. While writing that one, for example, I am writing the first and second carbon atom, means in the both the structure you can see that I am not going to change the any carbon atom. Okay. Simply I am going to move the only pi bonds. Okay. And number of unpaired electron, if it's unpaired electron is there, it should not change. For example, if you see the nitromethane, just now we already saw, I will go for the recap. So in this what nitromethane, what we have done here? Okay, now if you have lone pair, okay, here if you see the lone pair in the both the structures are same. Okay, and we are not shifting any atom. So for example, it's the first second oxygen atom. Okay, this first and second atom. Okay, nitrogen is in the same position and carbon also in the same position. So while writing the resonance structure, your nuclei, nothing but what? Atom you have should not be disturbed. Only how to shift the what? Lone pair of electrons and pi bond. Okay, so you have to follow these rules while writing the resonance structures. Here we have a note that among the resonance structures, which one is most stable? Just now we wrote for benzene 2. Okay, like that if you're writing the more than one structure, resonance structure, so among that which is most stable means, here we have the 3 points that you have to remember. Based on that you are going to tell which resonance structure is most stable. Don't worry, for based on this we have the example. I will go for the example also. First let me read now. The one which has the more number of covalent bonds means what? All the atoms with octet of electron except hydrogen, which has a doublet, means here hydrogen should have doublet, remaining all should have the octet. Okay, so if it is present, the resonance structure is most stable. First case. Second is what you can tell, less separation of opposite charge, means what? A negative charge if any on more electronegativity atom, a positive charge if any on more electropositive atom. Simple means, for example, you know very well, carbon having the more electronegativity, sorry, oxygen having the more electronegativity. So if it's not, and the negative charge if is present is more suitable. Okay, if for example we have the like carbon is there, okay, sometimes it's present if it is negative charge, if both are there, so in between the carbon and oxygen having the more electronegativity, so it is more suitable. Carbon a negative charge should be present and more electronegativity atom, and positive charge should present more positive atom, that is more stable resonance structure. Next what we have, more dispersal of charge is more stable than others, means separation should be there. Okay, what is that? I will go for the example. Let me go for the example now. Here we have the in-text question 12.16. What is the given? Write resonance structures of CH3CO minus and show the movement of electrons by curved arrow. Here we have to write the what resonance structure. So just now we told all has to follow what? Octet should be there except hydrogen should have doublet. Now if you write the structure here, this is the first resonance structures. Okay. Now resonance structures we are going to show with the double head arrow. Okay, here double. This indicating means what? Arrow, as you know well, if you show the direction, this means you have to move in this direction. If you show like this means you have to move in this direction, isn't it? So you are writing the like this means either the structure will move in this direction in this direction. Okay, so means these are two possibilities are there. So we are showing the resonance structure with the what? Double head arrow at two ends. Now we have to write the structure. Okay, so all having the octet, fine. Now as we told, while writing the resonance structure you should not move the atoms. So if you see here we have the carbon here. Here I am writing another structure, same carbon will be like that only. Here another carbon as such I am labeling this first oxygen atom, the second. So this is the first and second. Now I am moving the what here, only lone pair of electrons, pi bond. Okay, I am not moving any sigma bond. Once you move the sigma bond, what happens? There is a breakage of bond. So here just you are going for the one shifting of only lone pair of electron, pi bonds. Now already we discussed three movements. Okay, in the first video itself there is a three ways to movement of electrons in the organic reaction. Now here this is the case one, the pi bond is shifted to adjacent atom. Okay, so once it's shifted to adjacent atom means what happened now? You are going to get the pair of electron. Why? Because means one bond means pair of electron. Now you can see on this atom we have the one pair of electron. Okay, so here the second case is what happened, lone pair of electron is shifted to adjacent bond. So as you know very well, one lone pair of electrons are coming here means it's converted into bond. So now here this is converted into bond. Okay, so what I did here, I didn't shift any nuclei or any atom, just I shifted the lone pair of electrons and pi bond. In the same way you can write the structure from here to here. Okay, so here what happened, you are shifting the lone pair of electron to the bond, adjacent bond. So what happened, this pair of electrons convert into pi bond. Here you can see the pi bond. Now here what you are doing here, the pi bond is shifted to adjacent atom. So adjacent atom means you can see the lone pair. Now you can see the lone pair. So you can write the structure from here to here, so here to here. So this indicate means what? Resonance structures of acetate ion. Next, what is the question we have? Problem number 12.17. Write resonance structures of CH2 double bond CH indicate relative stability of the contributing structures. So first we have to write the resonance structure. After that we have to tell which is the most stable structure. Okay. Okay, this is a structure. This is a what you are writing the maintaining all are octet. Okay, around it octet except what, hydrogen should have the doublet. Okay, so this is a hydrogen having the doublet. This is the first structure. Okay, now for getting this structure, what I am doing now, this pi bond are shifting to this here, and this what, this pi bond is shifting to the as adjacent atom. So what happens, one shift here, this is bond is coming, this is you are going to break one bond, so this carbon going to get the here, this carbon going to get the positive charge here, and this double bond converted single bond, and single bond converted into double bond. Here you can see. Now once shift the pi bond to adjacent atom means you can see the one more lone pair of electrons and oxygen atom. Okay, so it's the second structure over. Now next what I will do now, this electron I am shifting to this carbon atom. Okay, after this pi electron I am shifting to this oxygen atom. So what happened, this carbon going to get the negative charge. Now this single bond is converted into double bond, and here we have the double bond converted into single bond. So once this double bond is not there, means the oxygen going to get the what? Positive charge on it. So here we have the three structures are there. Okay, this is first, second, third. Now among these structure, which is the most stable, means this is the most stable structure. Why? Because means the already we told most stable structure should have the octet. Okay, the most stable here, if you see the order, this is the first most stable, then second, and this is the third least stable. So why this order means, let me discuss now. So most stable, more number of covalent bonds, each carbon atom and oxygen atom has an octet and no separation of opposite charges. Here we don't have the charges and each having the octet except what? Hydrogen. So just now we discussed the rules here. So this is the rules we discuss, isn't it? Okay. The one which have more number of covalent bonds, all the atoms with octet of electron except hydrogen has a doublet. So it is the most stable. In given structures, among the structures which having the most stable, it is the most stable. So in the given example, so in this is the according to our what rules we have the, this is the most stable. Okay. Now second one, it is here if you see in charge here second one, negative charge on more electronegativity atom and positive charge on more more electropositivity atom. Here if you see, here we have the negative charge. Okay, here we have the positive charge. So as you know very well, oxygen having the more electronegativity, so negative charge present on the more oxygen atom and positive charge present on the less electronegative atom. So according to our condition, this is a second priority. And now come to third one, what happened? It's the least stable. Why? Because means in third one does not contribute as oxygen having the positive charge and carbon has a negative charge, hence it is least stable. So according that has what happened, according to our rule, more electronegativity atom should have the negative charge, but here what happened, oxygen having the positive charge, carbon having the negative charge, which is refers to this structure. Okay, so because of that reason, this is the least stable structure. Okay, here we have an word conjugated system. Okay, why we have to explain means next we have the resonance structure we have to explain. So before that we should come to know what is a conjugated. Okay, conjugation means what here? So conjugated means what? The presence of alternated single and double bond. Here for example I have the molecule. Okay, so here we have what? Alternate double bond is there, means it indicate means what? We have in the conjugation. Or sometime if you have for example instead of you have the alternate triple bond. Okay, this indicate means what? We have the what in the, it is called in conjugation. Okay, sometime what happen here, alternate double bond and triple bond. For example this is the condition. Okay, so here what I here we have the double bond after a single bond after that triple bond. This condition also indicating means what? It is in the conjugation. So alternate double bond and triple bond are sometime here alternate double bond and heteroatom having the lone pair. For example like this. Here we have the alternate double bond and heteroatom means I am taking the any halogen as a X. As you know very well, and halogen we have some lone pair. Okay, so here lone pair is there means what? Here we have the double bond and single bond after that lone pair. So alternate double bond and lone pair. Okay, lone pair and heteroatom. Heteroatom is what we told in organic chemistry, other than carbon, hydrogen we are calling as what? Heteroatom. So either you can take here what halogen or nitrogen or oxygen, whatever that may be. Okay, so this condition also called as what? In the conjugation. Next what? Alternate double bond and positive charge or negative charge or free radical. Here this is the condition. Sometime what happen here, you may have like this. Okay, so here what happened, we have double bond and positive charge. Okay, this also indicating means we have the conjugation. Sometime what happen here, we have the like double bond negative charge. Okay, so alternate we have double bond negative charge indicating conjugation. Sometime here like this. Okay, free radical. Okay, nothing but if you have any dot. Okay, this also indicating conjugation. Sometime what happen here, we have triple bond. Okay, here like this triple bond and heteroatom having the lone pair. Okay, this is the condition. If you have triple bond, one single bond after that lone pair means it is also indicating means what? Conjugation. Sometime again triple bond. Okay, having the what? A negative charge carbon atom, or if it is a positive charge or dot, this also indicating means what? it is a system in the what? Conjugation, nothing but molecule in the conjugation. So in an open chain, a cyclic system is termed as a conjugate system. If it like this present, all are indicating means what? The what? Molecule in the conjugation. Here you can see, okay, here we alternate carbon carbon double bond is there, okay. Here again we have alternated double bond. Here alternate double bond triple bond. Here we alternate double bond triple bond. Here alternate triple bond is there. Here we have alternate what? Double bond with either carbon positive, negative or free radical. This is what double with the hetero atom. So all this indicating what? The molecule in the conjugation. Here you can see the example. Acyclic means what? We don't have any cycle. Here you can see we have double bond, single bond, double bond, single bond. Means indicating means what? Here we have in the conjugation, the molecule in the conjugation. Now let us see the example in cyclic system means we have the ring, okay. Just now we saw acyclic means we don't have ring. Here you can see all these are example for what? Single and double bonds. Alternate here we have one double bond, single bond, double bond, single bond, double bond means up to here we have the conjugation. Now here you can see double bond, single bond, double bond, single bond, double bond means in the present what? Conjugation. Now here you can see double bond, single bond, double bond, single bond. After that here you can see up to here also, okay. Why? Because this total indicating means it total including ring, and this also we have in the conjugation. So alternate single and double bonds. These are the example for alternate single and double bonds. Now in this example if you see alternate double bond and heteroatom having the lone pair. Here you can see here we have the double bonds and heteroatom, okay. Heteroatom means nothing but we have the oxygen, okay. On oxygen we have the lone pair. So this also indicating we are in the conjugation. Here also you can see, okay. Here we have the heteroatom and single bond. Heteroatom having the lone pair, single bond, double bond means indicating in the total molecule in the what? Conjugation. Next here alternate double bond and negative charge. Here you can see double bond, single bond, negative charge, okay. After that again here negative charge, single bond, double bond means total in the what? Conjugation. Here you can see alternate double bond and positive charge. Here this is a positive charge, single bond, double bond, single bond, double bond, single bond, double bond means total we have present in the what? Conjugation. Examples for cyclic and open system. Here you can see in cycle here we have the double bond, single bond, double bond, single bond already is there. It is going to extend. Why? Because means here we have single bond, double bond, single bond, double bond, okay. Again single bond, double bond, single bond, double bond. So total alternate single and double bond as there, okay. These are the example for the having the cyclic and open system, okay.